Today I wanted to discuss the results of a paper I recently put up on preprint. It passed initial peer review, but I'm going to go with a different publisher because of the disagreements over copyright. But I went ahead and posted it online, and so I wanted to make my research available on video as well. And that's a calculation of the Higgs boson mass. The Higgs boson is a relativistic proton. It's not really a boson, it's just a relativistic proton. And the way we can determine this is by starting off with the relativistic positronium solution. If an electron and positron are orbiting each other relativistically, it forms a metastable state when the attraction between the electron and proton is countered by the centrifugal force that's pulling them apart. And there's two solutions for that. There's the regular non-relativistic solution that you find when you look up positronium. But it was discovered by Milne, and later Feynman and Sternglass rediscovered it, that there's a second solution that's relativistic. So at relativistic velocities, you have a smaller radius, much faster velocity, but you get a second solution. And the energy of that solution is 134.9766 MeV, which is the mass of a neutral proton. So essentially, a relativistic electron-positron is the neutral proton. And you get that with the multiple of 264.142 times the mass of the electron, 0.511 MeV per c squared. And this is close to, 264 is close to 274, which is 2 times the inverse of the Feynman structure constant, which is 2 times 137. And that's why the masses of all the unstable particles seem to occur in intervals of fractions of 137. It is because of this relativistic positronium solution. And that's what my Onium model of particles is based on. Well, if you substitute protons into the equation, which you can because there's nothing that says you can't, it still works. You get 264.142 times the mass of a proton gives you 247.8 GeV. And that's the mass of a relativistic proton-antiproton pair. And so if you have a proton-antiproton collider with sufficient energy, or perhaps a proton collider with sufficient energy, you should be able to produce these. And so I expect someday that it'll be announced that we have 247.8 GeV bosons that have been detected. And so we're probably on the verge of that. But if you had another case where you have a single proton, and a single proton could be relativistically orbiting an electron even, just a negative particle, it's charge-based more than it is mass-based if you have just a single in orbit, then you get half the energy, which is 123.919 GeV. Then, if you consider the case where you have a proton orbiting an antiproton, like I said, if you have a proton-antiproton collider, or if you're producing antiprotons because of proton-antiproton pair production, then you could conceivably get this proton-antiproton pair, and then you have to add back in the mass of the proton, which gives you 124.857, which is getting you really close to the measured mass of the Higgs boson, at least the initial one, of 125.18. Now, if you consider the case where you're not producing antiprotons through pair production, then what you might have in the middle is a negative sigma. A sigma baryon, which has 1,197.449 MeV. And if you add that in instead, you get 125.12 GeV per c squared, which brings you right up to the 125.18. And that is what they're watching at CERN. It has nothing to do with the Higgs theory, the Higgs boson, the Higgs mass, any of that. All that's nonsense. It's just a relativistic proton orbiting some sort of negative resonance, a baryon most likely. And in the paper I also discuss the WZ and the top quark, which are also resonances of this type. Basically, if you have a sigma orbit, you get the W and Z on the top. So anyway, I'll talk about those in another video. I just want to do one on the Higgs just for that. So anytime you're reading news on the Higgs, you know that it's nonsense. They called it the Higgs because it's just the fallacy of wishful thinking. It's what they wanted to find, and so they pretended they found it and tried to pull the wool over our eyes and fake it. Well, it's not really what they're seeing. Anyway, I hope you like this video, and if you do, please like it, share it with your physicist friends, subscribe to see my next video, and then I have my book on onium theory and particle theory, Goodbye Quarks, the Onium Model, and also a couple books on quantum field theory. And I'm a retired independent researcher, so buying one of my books helps support me in my retirement, so I appreciate it if you do that. And I also have a Patreon account. So thanks for watching. Bye.